Hello everyone, thanks for clicking on this video. I'm Chia-Yuan. I'm a postdoc working in the English Language and Linguistics department at the University of Kent, which is located at the southeast corner of England. Tamara and I are investigating rhythm in language. We are particularly interested in how people are entrained with speech materials, as well as what the acoustic features are important for such entrainment. So today I'm going to talk about our study, how to hit that beat, testing acoustic anchors of rhythmic movement with speech. In this study, we are investigating properties of the entrainment of language. We like to see when people are synchronizing with speech materials, what are the targets that they are aiming at. In our previous study, we asked our participants to tap along with tone sequences and syllable sequences such as B and boo. We found that when people were tapping along with tones, they were aiming at the tonal onset, whereas they didn't tap along with the syllable onset when tapping along with B and boo. Instead, their taps fell closer to the vowel onset. In a follow-up study, we tested our participants with repetitive English sentences. The sentences were repeated 20 times. We asked our participants to feel the beat and started to tap along with the sentences whenever they were ready. So this means that when they are tapping, the sentences were still ongoing. There were no specific target or instructions to tell participants where they should tap to. Other than syllable onset, we also tested a few different acoustic landmarks, such as the largest energy and the largest amplitudes, and we found that, again, people's taps feel closer to vowel onsets. So the results are interesting, however, may be incomplete. First of all, vowel onsets usually coincide with voicing onset and pitch, which perhaps can explain why the vowel onset become the tapping target. So we are wondering whether pitch is playing a role too. Secondly, it is not clear that whether our participants are synchronizing with vowel onsets or P-centers. For people who are not familiar with P-centers, it is referred to as perceptual center or psychological center. I will explain it a little bit more in the later slides. Thirdly, vowel onset had to be defined manually, but there are other acoustic landmarks that can be extracted more automatically. So in the current studies, we are exploring whether there are other acoustic landmarks that could be the target for people to synchronize with, and compare them with the performance of vowel onsets. So we chose 3 algorithms which generated 4 different acoustic landmarks. There are maximal energy increase, the max D. The location of it is approximate to epicenters. Periodic power plat, PPP, which considers the F0 frequency and periodic power simultaneously, and the empirical mode decomposition, the EMD, from which it will generate 2 acoustic landmarks which should represent the syllable and stress rate of the speech materials. I will introduce each algorithm and landmark in the following slides. So the reason why we have this maximal energy increase, the max D, is because a vowel onset usually appear with voicing onset and therefore with an increase of energy. So looking into energy increase of each syllable could be a good approximate replacement for vowel onset. So the max D was developed by Sturm and Volin. In their study, they asked their participants to pronounce a given word repeatedly, and they need to make the word sequence be aligned with a metronome sequence. The figure is an example of their results. The vertical dashed line is where the metronome locates. So they found that the max D is approximate to the metronome location, which is also the P-center. Previous P-center studies have indicated that when we are trying to make each component or sound in a sound sequence on the beat, we are actually not aligning them with each onset. Instead, we will make small adjustments, moving each sound a bit earlier so that we will feel the sound is really on the beat. The location where we are trying to align with, in order to feel the sound is on the beat, is the epicenter of that sound. However, previous findings also suggest that the epicenter of speech materials can be influenced by numerous acoustic factors, and it becomes very hard to control or monitor these factors in a more natural context, for example, in a sentence. So, the max-T offers a relatively easier way to find the approximate location of the epicenter, and it should be also not too far away from the vowel onset. So, the procedure to generate the max-D is to generate the energy contour first for the sound stimuli, and then do a difference wave of the energy contour to acquire the curve of the energy increase. So then just find the location of the maximum of that energy increase curve. That's why it is called max-D, the maximum in the difference wave. So the next one is the PPP. So because it has been shown that the F0 maxima can be the target of sensory motor synchronization in the core speech study, so we want to include an acoustic marker which considers the F0 frequency as well as the energy simultaneously. So the PPP algorithm is developed by Kenjimi, Albert, and Grice. They are very kind of letting us use their algorithm to process our speech materials. Their work combines prod and R script, and you can see example in this slide. So this is an example from our sentence stimuli, in which you can see that the curve of F0 frequency in pink and blue, and the smooth energy wave in gold. So you can also see that the F0 frequency wave only becomes salient when the energy is also relatively large. Okay. So the last one is the EMD, the empirical mode decomposition. So this is a data-driven method which decomposes amplitude envelopes of a sound wave. So the EMD decomposes the signal into a number of oscillations using an algorithmic sifting procedure. So they are called intrinsic mode functions. There are some criteria for finding such intrinsic mode functions, like the peaks and troughs are separated by zero crossings, the average of positive and negative amplitudes is zero at any point, so the functions need to meet those criteria to be intrinsic mode functions. Here's an example of the intrinsic mode functions of speech materials. In this figure, you can see that the first MF1 is the fastest time scale of oscillation, and then the second, and so on. So Chia-Yuan and Abiniti's paper, they proposed that the first two intrinsic mode functions, MF1 and 2, would represent the syllable rates and stress rates in the envelope. For example, they found that the mean within utterance instantaneous frequencies of MF1 was lower in English than in Greek and Italian, which is in line with the syllable rates relationship among these languages. And one of the main strengths of the MFs is that they are generated automatically. There's no need to do any annotation for the materials, which means one has little phonetic or linguistic knowledge is still able to employ the algorithm and generate the intrinsic mode functions. Right, so just a short summary. We have max-D, PPP, and two MFs as our acoustic anchors. We are going to see how they perform comparing with vowel onset on predicting people's tapping behavior. So here I'm showing an example of the location of each acoustic anchor. In some syllables, some anchors may be very close to each other, like the two IMFs here, while some may be separated further away from each other. Okay, so we have 6 sentences spoken by a young female with a standard Southern British English accent. Each sentence was repeated 20 times. There were short, medium, and long sentences in terms of different number of syllables. We have 29 native English speakers. None of them were musicians, but some of them did have some experience of music as well as dancing. Participants were asked to tap along with the repetitive speech sentences whenever they feel the beat. They were tapping on a percussion pad, then their tapping data were saved in MIDI format and then were extracted through a MIDI toolbox in MANAP. So this is the way we processed our tapping data. So Gaussian kernel density estimation was applied to each participant and each sentence. The figures here are the tapping data of each participant in our sentence 2. So the sentence was I took the prize. As you can see in the figures, the tapping patterns are different across participants. However, the tapping pattern becomes way more clear when we see the aggregated figure on the right. So this aggregated tapping data of all participants can help to find the pattern. So about the data analysis, firstly we calculated the synchronies, which is the distance between the tapping peaks of the tapping distribution of an individual and the closest event. So here's an example. So the figure is an example of the participant's tapping distribution of sentence 2, I took the prize. And you can see that the tapping peaks are located for the tapping distribution, and the sentence I took the prize, the acoustic landmarks are located too. In this case, these are vowel onset. Then the distance between each acoustic event and each tapping peak is calculated as the synchrony. So for each acoustic event, there is a synchrony. So the normalized number of taps is more straightforward. The number of taps appeared around the event was counted, plus and negative 120 millisecond window applied. Then this number will be divided by the total number of taps for the individual on that sentence, so that we could get the percentage of taps that the acoustic event attracted. We ran linear mixed effect modeling for the asynchronous and the number of taps respectively. For each model, the acoustic landmarks was the fixed predictor, and we ran 4 planned comparisons comparing the vowel onset with other 4 landmarks in each comparison. So results. Our results show that vowel onset performed better than other anchors, except for max-D. There was no difference between the max-D and vowel onset in terms of asynchronous. And the number of taps. The result of percentage of the number of taps showed that vowel onset performed better than 2 MFs, but it only performed marginally better than PPP was because of the buffer correction, because there were 4 comparisons there. Right, so the discussion and conclusion. Well, in summary, the vowel onset outperformed other acoustic anchors in terms of asynchronous and number of taps, but the vowel onset is not better than the max-D. So compared with vowel onset, max-D could be a good alternative as it is not defined manually, and it can apply to a syllable which does not contain any vowels such as sonorants. The PPP max product of pitch and energy did not perform very well in terms of asynchronous. However, the current study used a 50-50 weighting for the F0 frequency and energy. So perhaps the weighting can be adjusted in the future to find an optimal performance for the PPP algorithm. Both MFs were underperformed. It could be because that although they are capable of capturing the syllable rate and the stress rate of the sentences in general, they are less sensitive to a specific acoustic feature at a certain time point. However, they are the most automatic algorithms. They don't need any annotation of the speech materials. In the current study, both MaxD and PPP still acquired syllable boundaries so that a local maximum could be located within the syllable. So there's still potential for MFs. So to conclude, perhaps the MaxD is the best alternative for the vowel onset that people are synchronizing with repetitive sentences. However, only 6 English sentences were included in the current study, so more sentences and perhaps in different languages should be included in the future research. Right, so that's it. Thank you very much for your attention. Thanks to my PI Tamara Rathcke and our collaborators in Montreal, Simona Falk and Simona Della Bella, and thanks to Speech Prosody Conference for organizing the virtual event. That's all. I hope every one of you stay safe and healthy in this difficult time, and hope to meet you in person in the near future.